Kelsey go home early?
She's going to. I want her to stop by because she needed notes, and I had nothing prepared. Okay, we have shortened periods today, so we'll do the best we can. So for the do now, we're asked to find the area between the graph of y equals x cubed and y equals x. Oh, I missed it a little bit. Perfect. So we're looking for this region just over here. There are actually two regions enclosed, but you're just asked for the area in the first quadrant. So the way that we were finding the area on Thursday, we summed up using a definite integral the areas of an infinite number of rectangles, and we used vertical strips. And when you use vertical strips, to get the height, it's y top minus y bottom. And do you remember what the width was when you use a vertical strip? Dx. That's what we use. Now in this case, when you're in here, what does y top equal? X, right? Because you can't look outside or it's going to mess you up. So this is the graph y equals x, this line up here. So y top is x. What about y bottom? That's x, y equals x cubed, so that's just x cubed. Dx. And you might think, oh, that dx, who cares? Who cares about that dx guy? You care, and some other people care because, you want to get that right. That tells you the only variable you're allowed to use in this problem is x. So even though we say y top minus y bottom, it's in terms of x. And for the limits of integration, you want to add up these rectangles starting from the smallest x coordinate to the greatest x. And when you want to find out where two curves intersect, you got to set them equal to each other, right? So for the limits of integration, if we set, bless you, what y equals on one curve is x cubed, and on the other, it's x. So when they intersect, they're the same. Is that a question? Okay. And now we're going to get it equal to 0 and factor, what we always do. So if we subtract x, I want to factor this so I can solve it. Pull in an x. So you have x times x squared minus 1. Dots. I'm going to go with this. Extend the page. I'm just going to go down here. So I have x times x plus 1 times x minus 1 equals 0. X equals 0. Nice. We have three values of x because there are 3 points of intersection. So over here, the x coordinate is negative 1. Here, the x coordinate is 0. And over there, the x coordinate is 1. Now, we just want the region in the first quadrant. Yes, Ryan, what do you think? Yeah, since we just want this region here, tapping it for the kids at home so they see it. Yeah, our limits of integration are going to be 0 to 1. We're adding up these vertical strips from x equals 0 to x equals 1. That's the setup. That's the hard part. Now it's just, so let's get the antiderivative. What do we get for the antiderivative? Nice. And we plug in the upper, the lower, and we subtract. Okay. When we plug in the upper, the 1, what's the first term? 1 squared over 2, 1 half. And then we plug it into the next term, bless you. What about when we plug in the lower limit? What happens to both terms? 0. 0 squared over 2. So you could write them separately. I'm just going to write 0. So what do we get? Half minus a fourth. 1/4. Because 1 half is 2/4. So when you have 2/4 minus 1/4, you get 1/4. So we just found that the exact area of this region up here is 1/4 square units. Pretty cool, huh? That's good enough. That's the 24. Got it? square unit. Like if this was, if on the x-axis, yeah, if this was a foot, it'd be 1/4 of a square foot. You know, depends what the units are. Square units, I will say. Alrighty. As far as the homework goes, I did put the answers really tiny on the back if you turn your paper so you can check your work. Check that you set up the intervals. Okay. Line out. What? You don't have them? Okay. So, look through the answers, see if you have any questions. Yes. Number 5. All right. Well, I guess it's better than asking for 6. Okay. Number 5. They didn't even give us a graph. We had to get our own graph. Nice. So we want to get the area between the graph y equals the cube root of x squared. Oh, no 1, 1 is on it. Squared. I'm just thinking if there's anything good I could do here. So I know it goes like this somehow. This is not exact. That's just a sketch. It's the seagull graph. Yep. And then y equals 1/2 x. That's just the line. Yeah. Don't go by my graph too much, but you know, starting here at 0, up 1/2, up 1/2. So, oh, I don't think that's good, to be honest with you. All right, but the idea is we want this little region in here. We want the area of this region in here. Little area. So the way we get area is we always use rectangles. I mean, that won't change. Area is the sum of height times width. And if you're using vertical strips, which we will, you need y top. And you don't have to write y top minus y bottom. I'm just writing that here for you. We got to fill in what those functions are. So if you're in here, what does y equal? Cube root of x squared. Y top is the cube root of x squared. And y bottom, 1/2 x. That's the other one. But we need our limits of integration. We want to add them up. I just really rough sketch this. To find out where they intersect, we're not going to go by this graph. We're going to set the functions equal to each other, solve for x, right? So to get our limits of integration, we're going to set the cube root of x squared equal to 1/2 x. Find out where they intersect. I mean, I already know that one's 0. I'll pretend I don't know. So you have the cube root of x squared has to equal 1/2 x. I don't like that cube root. How can I get rid of that cube root? Look at me. Okay, you can make it a fractional exponent. Cube both sides. Let's do that. Let's cube both sides. So we have, if you cube the cube root of something, you just got the what's underneath there, right? And if I cube 1/2 x, what do you get? 1/8 x cubed. Yeah, we cube both sides. I can't scroll down on this one. Yeah, let's multiply both sides by 8. Now, what am I going to do? 8x squared equals x cubed. Yeah, we want to get it equal to 0. Gotta go somewhere else with this. So if we bring the 8x squared over, I'm just going to go to my other screen just for a second. I have no room. Yeah, I got a lot of things open. Wait a minute. I'll just go to this one. It's nothing. Okay. So we had, tell me what we had when we had x squared equals, we had 8x squared equals x cubed? Yeah, okay. So we'll get it equal to 0. So I have x cubed minus 8x squared equals 0. We'll factor out the x squared. minus 8. So our solution, x equals 0 and x equals 8. All right, so those are going to be our limits of integration. And so if I go back here, yes. Yeah, you can do that, but you also have to be able to do things without a calculator. But yeah, you could have done that one with a calculator too. So it would be 0 to 8. See, yeah, my graph was a little off. Were they? Right. I said it wasn't perfect. You don't have to like dig in. But then, so that was probably the part that got you getting limits of integration, or was it after this part? So you actually got the antiderivative. You did this the long way, or did you plug it in the calculator? What? Who does that? No, that's nice. All right, I'll try to do it real fast. Let's see. Okay, so this is an x to the 2/3. So when you take the antiderivative, what do you get? How about 3/5 x to the 5/3? That sounds good, right? Yeah. Guys, what do we get when we integrate 1/2 x? I think this is the problem. 1/4 x squared. Okay. We're doing this one by hand, using the FTC. I'm leaving just a little bit of room to plug in the 0. Okay, let's not go to the calculator then. Let's just do this. If you plug in the 8, first let's take the cube root of 8, which is 2. 2 to the 5th? You want one too many. 32. So I have 3/5 times 32 minus 1/4 of 8 squared. What's 1/4 of 8 squared? 16. And when you plug in a 0, you just get 0. So 3/5 times 32, that's a lot of fifths. For the 96 fifths. All right. Now where am I going with this? So we have 96 fifths minus 16 for our answer. Okay. We have 96 fifths minus 16. We need a common denominator. 5 works. So we have 96 fifths minus 16 times 5. 85th. Giving us an answer, 16/5. Nice answer. 8.2. Right. Oh, you like that one? You don't like that one? Okay. Good. Alrighty. So now, do you mind if I just go on and I just do this? I know I might try to rush into homework, but yeah. Okay, so you say, wow, I always want to use vertical strips to get area. Where am I? But, yeah. Oh, this is us. Do you remember the other day, Thursday, do you have those notes available, day 71? Look at the very last page. We didn't do it, but I had it set up. Okay. Here's the thing. Whoa. Nothing happened. Can't see stuff. Vertical strips sometimes are not going to be the best way to go. It's not that you won't be able to do it. Well, sometimes you actually won't be able to do it. But sometimes it'll just be more convenient to use horizontal strips. And I have an ugly example here. But I have most of the work done for you. We're just going to fill in the little pieces. But just to illustrate why sometimes you want to use horizontal strips. Suppose you have the graph of x equals y squared. Do you know what that graph would be? X equals y squared? Well, that's half of it. What do you know the graph of x equals y squared has to be? What do we call that graph? It's quadratic parabola, right? It's just that Now the y squared instead of the x, so it's sideways parabola, right? So when you want to solve for y to graph it, you solve for y squared equals x. That means y equals plus or minus the square root of x. When you want to put the graph of x equals y squared in your calculator, you have to put it in as two separate functions because that's not a function. So you have to put it in as the square root of x. The square root kind of got blocked off. That's the square root of x. And then the negative square root of x, just to get that one graph. The other one's also a parabola. So if you go ahead and you solve for y, you're going to get plus or minus the square root of 3 minus x over 2. So if you want to see these two parabolas in your with your calculator, you have to enter them in it with 4 functions. And I just want to show you what that looks like. So you've got this. If you only graph this positive square root of x, you would only see half the parabola. That's the positive square root of x. This part down here, right, is the y equals negative square root of x. Then you've got the top half of the parabola over here. That's the positive square root of 3 minus x over 2. And guess what this graph down here is? Yeah, that's y equals the negative square root of 3 minus x over 2. So now we can see it, and we want to get the area enclosed by these two graphs. If we just tried to use vertical strips, which we've been doing, we're going to need two separate integrals. One integral to get the area of this light color here is green, this green region. And then I need another definite integral to find the area of the second region. And the reason you're going to have to do that is because, you know, like we take y top minus y bottom to get the height of a strip. What happens when we hit here? Whoop, y top changes from one function to another. We need two separate ones. Now I've given you I've labeled the important x values where they intersect. The x coordinate's 1, over there it's 3. So let's go ahead. Let's say we're going to use vertical strips, and we want to get the area of the first region. If I draw a rectangle in here, a vertical one, the width is dx, but what's y top going to be? Square root of x. And what about minus y bottom? What's y bottom going to be? Negative the square root of x. So the heights of these rectangles in this first region, positive square root of x minus a negative square root of x. What is square root of x minus negative square root of x equal? Okay. But we'd add up those rectangles from 0 to 1. Those would be the limits of integration for the first region. And that would get me the area of that first region, but then I have another definite integral to get me the area of the second region. Can you tell me what y top would be for any rectangle over here in the second region? Radical 3 minus x over 2. And what's y bottom? Negative that. Over 2. And we could clean it up, right? We could combine these. If you have a rad minus a negative rad of whatever, what do you have? You've got two of them. 2 rad 3 minus x over 2. But do we all agree that's kind of a lot of work? Do you guys like getting out of a lot of work? You like taking the easy way out? Yeah? Sure you do. All right, so go back to today's notes, and we're going to do the same problem. I'm not going to finish it up doing this way it's doing. But we are going to do it using horizontal strips. Dave? I know, it's not going to happen, but, well, hopefully you'll get the gist. Yeah. Remember the other day when we were talking about the area of a vertical strip versus a horizontal strip? We actually did look at how you would find the height of a horizontal strip. Does anyone remember how we did that? For vertical strips, we use y top minus y bottom. We took it was x. You take the x coordinate over here on the right, and you subtract whatever x equals over here on the left. And the width, if we're going to use a horizontal strip, is not going to be an infinitely small change in x. Yeah, it's going to be dy. It's going to be an infinitely small change in y. So if you have two graphs that intersect, and you want to find the area enclosed, you can use horizontal strips. It's just that you're not going to use y top minus y bottom. So if this function here is x equals some function w of y, and the parabola here, the one on the left, if that has an equation x equals v of y, oh, why am I not over here? Then we can actually find the area enclosed by summing up, that's the definite integral. This is your x right, x, whatever x equals on this graph, that's your x left. The thickness or the width of each strip is dy. And for the limits of integration, you want to go, you don't want to add them up from left to right, you want to add them up bottom to top. So you need to add them up from the y coordinate of the lowest point, which I'll call C, to the y coordinate of the upper point of intersection. Yowza. All right. Let me just draw them in. This is going to be a fail. I'm feeling a fail coming on here. All right, so this is the... Darn it. Kids are sad.
I'm so sad.
I'm sad. If I were you, then start on your take-home quiz, because you can do every one, I think, except for the last one. I don't know if you're going to be able to. If you want to try to set a couple up, I think tomorrow's lesson, I'm going to switch it to finishing this lesson. Okay. Kelly, bye, guys.
With the Sourman students, please come to the guidance office. Dylan Bush, Stephanie Sutherland, William Rivera, Brianna Mescal, Jose Maldonado,
Area equals the sum. X right is 3 minus 2y squared. X left is just y squared. And you have to add them up. I'm adding these up. From y equals negative 1 to y equals 1. That's the basic setup. Good luck to finish it tomorrow.